Hello, everyone. And first of all, thank you for joining. And also a huge thanks to Current FM for arranging this. My name is Farzane. I'm a musician, researcher, sound artist. I'm from Iran, but I'm currently based in the Netherlands. My main focus is on experimental electroacoustic music, and I was classically trained since I was very young. So now in my work, I use acoustic instruments, programmable instruments, field recordings, creative coding, and live electronics. Um, so this is a very brief background. Today, the session is about an introduction to data-driven composition. So maybe first I should mention that during this session we're going to talk so much about theory, maybe most of the time, because I believe when we want to use something as a tool or as a technique, it's essential to know some terminology, to be familiar with the tools and techniques that we're using, so that it will be easier and most efficient when we're actually using them. We're gonna talk about theory again, and then after that we're gonna dig into some aspects of aesthetics and sonification design, and then we're gonna take a look at some very good examples of data music and visual also in some case. And in the end we're gonna take a look at some small snippets of code in SuperGlider from how I approach sonification. So the codes are quite simple, and yes, just to get an idea of the approach that I have. So before everything, I should mention that most of the contents that I would be presenting today are beautifully collected in this sonification handbook, which is great. So I will be referring to this book so much. I've extracted some graphs and pictures that we're going to see later. But if you find yourself interested in sonification, I think this is a very, very good source to start with. So, yes. So in theory, we have to speak about some definitions, terminologies, taxonomies. We're going to talk about data properties and task dependency, what they mean, how we use them in our creative practice. And yes, so first to break down all the, to break down what we have to actually define, we have this graph, which is again extracted from the sonification handbook, which is showing a very basic communication system. So on the left, we have the information source, so the data itself, and then we have the transmitter or the communicator, and then of course at the end we have the receiver. So for example, in the case of a phone call, I would be on the left, the telephone is in the middle, and my friend is on the right. Or in the case of a graph, a visual graph, we have the data. For example, we have a graph of the percentage of, I don't know, male and female in participating in this workshop. That is the data. Then we have the communicator, which would be, in this case, the visual display, the graph. And then the receiver on the other side would be our eyes, that we can see and perceive the information. So this is the building block of a communication system. Now we're going to talk about auditory display, which is one of the most fundamental definitions that we have to check out. So auditory display, what is it? Any kind of display that uses sound to communicate information can be classified as auditory display. This is a very broad definition, but I think it's well put together. So again, any kind of display that is using sound to communicate information. So, for example, the researchers who are working with auditory display, what they're doing is to examine how the human auditory system could be used as the primary interface channel for transmitting information. and the goal for that is, of course, to understand better the changes, the structures, and the relations between the data that we're observing. And why should we use auditory display? Well, I think the most important reason is that the human auditory system has a very nice capability of detecting complex structures, even at the same time. So even if you have multiple layers of complex temporal changes, you can make a distinction between the layers and connect them and have a better understanding of the whole picture. So, but there are also some practical reasons of using an auditory display. For example, in the case that, for example, the other portals could be busy with another task, or if the person is visually impaired, either physically or as a result of an environmental, like for example, fog or smoke, then you can't really see. So then auditory display could be more useful. For example, another reason is that in high stress situations, human system is more sensitive and actually reacts faster to sound. For example, in running matches, they usually use a gunshot to declare the beginning of the match. And one reason that they do that is because the time that the brain processes this, that okay, there's a sound and I have to start, this becomes shorter than if they would get the sign with the visual elements like a green light, for example. So these are the practical reasons that we can use an auditory display, not artistic ones, of course, but the practical reasons.
Excuse
yes,
me.
so, and again, this second part is explaining more what I said about the ability to, for us to perceive complex patterns in time better through sound.
Hello, Farzane. 1 second.
Yeah.
Are the pages moving in the presentation? Okay, I think now it has, but before it wasn't moving, I think.
Oh, really? Oh my God.
But now
okay.
we are on page
We'll
7.
Like, maybe. Yeah. Okay. Now you can see it, right? Okay, damn. So this was the communication system, because I think you didn't see it. We have the information source, the transmitter, and the receiver, the graph from the sonification handbook. Then this is the definition of auditory display. It's pretty much what I just said. So I think the most important part would be the first 2 lines that are giving the definition of an auditory display. And then we have sonification. So sonification could be classified as a subtype of auditory display. So sonification is the technique of rendering sound and actually translating the data relations that we have in our data set into relations in our acoustic domain perception. So sonification is just the technique within that auditory display method. We have another definition by Kramer, which is also referred to so much in that book. So the use of non-speech audio to convey information, and yes. Herman in 2008, he did a research, and as a result of that research, he specified some conditions for a sound to be called sonification, which I think is very useful. So data dependency, which is clear, objectivity, systematicness, and reproducibility. So it means that if we have the same data set and if we're using the same technique, then we should be able to end up with the same result. Yes, let's go to next. Okay, so we have to classify sonification. We have 2 main ways. We have 2 main approaches to the taxonomy. One is to do it through the function of the display, and one with the technique of sonification. So these categorizations are not like they're not negating each other, but they're just two different approaches in the taxonomy. So we're gonna talk about the functions first. So this approach. First, we have so based on functions of what we want the sonification to do, we can categorize it. So the first one would be alarms, alerts, and warnings. In this case, so for example, the notification alarm of your phone saying that you have a text message, or the microwave saying that the time has ended. These are in the category of alarms, alerts, and warnings. They have some specific, for example, they are usually very simple, overt, and they're information poor. So they just give you the hint that something happened, an event has happened, but they don't really give you that much information about the state or about what actually has happened in detail. For example, in the case of the microwave, if you hear the beep, you understand that, okay, the time is over, but the beep doesn't really tell you if the food is cooked or how much the temperature it is at that moment. So they're very, very simple and overt sounds that just give you the hint that something is going on or something has stopped. The other one would be the process or the monitoring. So you're monitoring and observing changes in data over time. For example, in hospitals, patients who are like in critical care or intensive care, they're hooked up to all of these machines that the doctors can use their auditory system to detect what the patient, how the patient is feeling. For example, the heartbeat is assigned to a beep that if the time gap between those changes, and then they know that, okay, the heartbeat has changed. So this is just for the sake of monitoring and seeing the process, observing the whole process. The third function would be data exploration. So when we want to have an understanding of the data set that we're translating, we have data exploration. So the difference between, for example, data exploration and the monitoring might be a little vague. So I can say that in data exploration, we have a more holistic approach to the whole picture. So we're seeing the whole change of the data set within one picture. While in monitoring, we're just in monitoring and in alarms, we just have a momentary picture of what's happening. And then we have art, entertainment, sports, and exercise. That, of course, it's our probably it's the most interesting part for us here. And there are a lot of examples that we're going to talk about in depth in a few moments. But yes, there are also a lot of examples, for example, in sports, when there's a soccer game between the visually impaired and the sighted people. They usually use auditory displays and sonification to give the necessary information to the players. Or the system of biofeedback or this kind of stuff, they all lie within the last category. So if you want to do the taxonomy in another approach, so we did here with functions, and now we're doing the categorization based on the techniques. We have three main techniques, which is event-based, model-based, and continuous. So event-based, it's something like the alarm. So usually there's no interaction from the receiver required with the system. It's just to give you an information. So it's like the alerts of the microwave. And then we have model-based, which is a more complex one, which creates an artificial model that the user can interact with, and then the system would give back data, again, interact with the user. So for example, maybe a virtual instrument could be categorized as a model-based sonification, where you have the model of an instrument, of a synthesizer, then you interact with it, and because of the relations between the variables of that model, it gives you something back. So you played this, I'm gonna make this sound. So this is a more complex one that is more structure-based, the model-based technique. And then we have continuous, which is in fact dealing with the time series and sample data. So just to have the trajectory of the whole structure of the data and the patterns. So the data is directly translated into sound, whatever data it is. Since it might be a little bit vague, we have an example here. So audification, for example, is a very, very famous example of continuous sonification, which, yes, the waveforms of periodic data are directly translated into sound. This is again by Kramer. So this is an example of something that Michael Chinen made. He's a software engineer. This thing is using audification, and it's called fucking web browser. I'm not sure if it's still working, but there's a video on it on Vimeo, so I'm gonna play this video a little bit so we have an idea of what continuous sonification and audification is. Oh, what was happening there is that he was converting the memory server, the data from the server memory directly into audio. So what we call audification. This is a nice example. You can use this link to go read about it a little bit more. Now we're going to talk about data types, because we're dealing with data, so we have to know some basics. So what we're, as musicians, mostly interested in is to discover the relations between the data points and then translating them into sound. And then we have to consider some aspects of data and task that we will do in a minute. So we can classify data and the types of data in various ways. So firstly, information can be classified as quantitative or qualitative, which I think it's pretty clear, but it's like saying 85% of the time or saying often. So you're using numbers or you're using a qualitative term for it. Then we're dealing with nominal data. That is mostly dealing with the groups, I would say. So gender, nationality, language, style, these will be all under the category of nominal data. We then have ordinal data, which from the name it's kind of clear again, but we're dealing with numbers and rankings. So first, second, orders. And then we have ratio and interval data measures that, for example, something like scales could be classified under this category because scales are some, so it's the interval between the notes that are defining the scale. So that's the data type that we're dealing with. We have to talk about task dependency a little bit. I'm not going to spend so much time on this, but it's very useful because when you're doing sonification, there are some considerations that you have to make. For example, with this sonified information, what is the user expected to do? How much information does the user need to fulfill that task that they have? Do they have to do anything? Do they not? How much information they need? How much information is being transmitted to them by our sonification and this kind of question? So it's essential to know a little bit about task dependency and types. But yeah, again, not that much time. So in monitoring, monitoring is just the idea of making distinction between different sounds and then observing the events that are happening in that environment. For example, if you're in an office, there are a lot of devices that are making sounds, alerts, warnings, all kinds of, like phones, fax machines, computers. And your task here in the monitoring section is only to make a distinction between the sounds. So, okay, here's the beep of the phone, here's the fax machine, and just making distinction would be enough in monitoring task. Awareness of a process or situation could be environmental situation that you're in. For example, soundscapes are a very good example of this kind of task. So you're in a specific environment, you are getting information from what's going on around you, and then you're aware of the changes because you have a standard to refer to, or you know the range or what the changes in the sound mean in this case. Then we have trend identification, which is, again, I'm missing an I here, sorry. Trend identification, which is just to observe and study the patterns and the structures within the sonified data. And then just exploring whether the data is, whether what you're hearing, the data points, they're ascending, descending, what is the relation between them, and so on and so forth. And dual task performance and multimedia task scenarios. So this gets more complex. So it's the question of, okay, if I'm playing a musical phrase, and then at the same time a speech recording is being played, that would be multimedia tasking scenario. So you have to understand the speech, and then you also have to make a distinction for the scale and this kind of stuff. So it gets more complicated. I'm not gonna spend so much time on this. Then we get to data representation categories. So we have discrete, continuous, and interactive, and we're going to see what each of these mean. Discrete, or what we call DDRs. So discrete data representations, or abbreviated as DDRs, are where the data points are sonified in the individual auditory event. So for example, I have number 1 to 7, and then I have note C, D, E, blah, blah, blah. And then whenever I get number 2, I have note D. Whenever I have number 5, I have note G. So this is treating the data sets and sonifying it in a very discrete way, not as a whole thing. And then we have continuous, or continuous data representations, or CDRs, that are continuous. So, and in this case, they have two preconditions that we have to consider. So one is having an equally spaced metric in at least one dimension, and from the other side, sufficient data to be able to have the minimum resolution that we need for perceiving the data relations. So yes, and they're used mostly to explore the system that that produced the data. Then we have interactive, which is more complex, maybe. So the relations between the data points could be changed in an interactive way. I will make an example to make everything more clear of this is called Interaction. It's a collaborative work that I did with Arash Akbari. It's an interactive audiovisual installation where in a very brief way, I would say that we have autonomous agents in the space, and then as the user walks in, they start to interact with the user. And from the sonification side, which is what we're dealing with, and is what I was doing was that we had, for example, 20 agents in the space. I was taking the X and Y position of each of these agents and then sonifying them, so assigning them to a parameter of my sound. A simple example would be that you have a point moving in space, and then you take the X coordinate and you assign it to the pitch, you take the Y coordinate, you assign it to the amplitude, so something like this. But yes, in this case, I was using different methods and techniques, for example, granular synthesis. And then since there were lots of agents, then you got all of these emergent behaviors from the sound. We can see a short video of it. I hope the video wasn't too laggy, but yes. And another thing that might be interesting in this to mention is that the way the user was behaving in the space would change the functionality of the data that we were receiving. For example, if you're walking very slowly or not moving at all, then they would behave differently, the agents, and therefore the functionality of the sound would change, just to be able to play with the composition structure, I would say, in an interactive way. So this was an example. And then for a short time, I think it would be nice to talk about representation, data representation and mappings. So how acoustic perception takes on conceptual representation. So we're gonna speak a little bit about semiotics, which is technically the science of signs. So how we associate a sound to the sign that it's the sound of a sign to what it's representing. And there is a very nice, so I think Stevens, if I'm not mistaken, in 2004 made a classification of representations. So it was direct, indirect ecological, and indirect metaphorical, which you can also see here. So what do they mean? So direct means, so if there's the sound of the wind, then it's representing the wind. So direct, the sound of the wind has this sound. So when you hear it, you directly associate it to the source, which is the wind. Indirect ecological would be different in the sense that, for example, they don't have direct associations, but they somehow influence each other. For example, in the case of the wind, you have the sound of the wind, but you also have the sound of the branches and the leaves, like, moving. So the sound of the leaves moving may not directly represent wind, but you get the idea. There's the wind, and then it makes the trees move, so we have the sound of the leaves. So this is indirect ecological. And then we have indirect metaphorical, which is, again, for example, we have the sound of a fly flying and associated with the sound of a helicopter. This would be a more simple metaphorical approach of classification. And then on the other hand, we have the iconic approach, which we use an icon to represent something. For example, we use earcons to represent an ecological relationship. As an example, on our computers, we all have, for example, an icon of a trash or a recycle bin that looks like a trash bin, and it's just the association you make within this is a trash, and then I'm throwing something away. So this kind of iconic association would be like this. But not the problem, but I would say what we have to bear in mind is that especially when we're dealing with interacting with the computer, for example, maybe we cannot really associate a specific event to a specific sound. Yes, we can have the recycle bin, and whenever we empty it, we hear all the papers being thrown away. But what sound would we associate with, for example, save as, or things like this? They usually require no or minimal learning, so it has to be. It's an iconic approach again. And then, of course, we have to talk about mapping, which is probably one of the most important aspects when we're talking about sonification. So what is mapping? Mapping is the conversion of one form to another. So if I'm using the data from the temperature to assign to my frequency, then there's the mapping of the degrees in temperature to my pitch classes. So this is what mapping means technically. And there's a quote from Ariza, which is interesting, that says mappings are often more important than what is being mapped. So this is where it gets kind of tricky in the mapping, because sometimes you would think, okay, I'm getting some data, and then I'm just gonna assign it to something, and then I'm good to go. But this is not usually the case. So even if you have sensors, receiving the data and then assigning it to something is usually the easiest part. But the challenge here would be actually the mapping and the scaling and calibrating the data that you're receiving so that you can actually use it in what you want to use it. So mapping, again, is a super important aspect. And then it's nice to know what data bending means. I'll just read. Data bending refers to mappings of data to musical parameters where the musical output is most valued. So when we're thinking about the aesthetics and the musical value and the artistic value of what we're ending up with, we might have to manipulate the data in order to end up with the desired result. And that is what we call data bending. So about mapping, there are some considerations that we have to bear in mind. The most important characteristics are usually density and polarity. So the density of the data points of what we're taking it from, of our data set, and then translating it into our certification, into the auditory display that we're making. And also the polarity. So for example, if the temperature is, if you're boiling water, then the temperature is increasing. And then if you want to assign it to the frequency of a sine wave, then it makes more sense, I think, if we assign it from low to high. That's usually how it's done. But the idea is that the polarity is also very an important characteristic of data sets that we have to consider when we're dealing with the mapping. And then we have Baras. I'm super sorry for mispronouncing. So that had an idea that, I mean, as a result of his research, said that nominal or categorical data types could be represented by categorically changing acoustic variables such as timbre. And something like interval data may be represented in more continuous variables such as pitch or loudness. So here we see why it was important to know categories of data, so that now that we're using it as a tool, then we have an idea of what's going on. So, and yeah, of course, some patterns and some polarity considerations are more common. For example, pitch is considered good for, or efficient for representing temperature changes. While if you use tempo to represent the changes in temperature, it might not be as effective. Parametric mapping. So data dimensions can be mapped to sound parameters in different ways. For example, we're dealing with physical characteristics, which would be frequency and amplitude, psychophysical, which is pitch and loudness, perceptually coherent complexes like timbre and rhythm. So, so if, again, like the example of the installation, so if you have many data coming in and then you want to make sense of the whole picture as a whole, as an entity, then you have to consider what kind of mapping from what data to what parameter would be the most efficient. What, first of all, what your goal is from the sonification, and then accordingly you specify the mapping strategies, I would say. And then, of course, we simplify the data, we use data bending, and this kind of stuff according to what we're dealing with. So firstly, we have to know our goal from the sonification, and then accordingly we set the tools and the parameter techniques. Yes. And then auditory streaming, which is dealing with how many concurrent streams does the data set suggest, and how we can actually show that, or in a way that they are all perceived at the same time, or are we more emphasizing on the relations between these data sets and all of these sounds and streams. So this is called auditory streaming. You can read about it more. And then finally, we're kind of over with the theoretical, boring stuff, maybe. So we're gonna take a look at some examples in music. and see how different artists approach this sonification and data music. So the first thing that we have to bear in mind is that when we're dealing with data in order to make music, or where again the musical value is evaluated, then the whole strategy changes, because then it's not just a matter of giving the most clear and most I would say loyal data to your data set, but also the aesthetics become important. So it's like a different approach to dealing with data, and this is something that we have to consider. So it's different from having a scientific model or a graph of something, which its job is to just depict something in a very strict way. And then Larry Polanski had the idea that the approach to experimental music itself is some kind of sonification somehow. So the idea of having this hypothesis and then ending up with a piece of music when you're doing experimental music, it's somehow a process of sonification all by itself, which is an interesting point. So this is on this side, and then on the other side, you have more complex cases where the data is driving more parameters that affect decision making, development in time, and the compositional structure. So this is a quote by Curtis Rhodes, which is again talking about how, so if you look at the last lines, is today artists sonify data from diverse sources, blurring the lines of artistic and scientific projections. So again, talking about what your goal is from sonification, knowing that, and then finding your right balance between the scientific and the artistic field. So one work that we're going to listen to is by Larry Austin. He's an American composer. He was an American composer. I think he passed away a couple of years ago. He used a map of Canadian coastlines and then extracting fractals from that map, and then using these coordinates of data to control compositional algorithms. So melodic contour, interval choice, textural density, dynamic flux, and rhythmic design. And this was, and yes, the tape voices were designed and generated in Synclavier Digital Music System at the University of North Texas in Denton. So this is the map. And the fractals, he extracted fractals from these lines, and then he used the data to sonify. This is quite long, so yeah, let's start listening to it. Okay. Um, I hope you can hear me. Yes, I think so. Okay. Oh, okay, great. I'm glad. Okay, so the next thing we're gonna look at is Ryoji Ikeda, which is probably one of the most famous sonification um, people. I'm not gonna explain so much. This is a video, so and yeah, there's enough explanation in the video. So let's just.
Test pattern is just pure conversion of data to sound. You're experiencing just binary patterns. If you convert even very small email or data onto the ultimately the build of the zeros ones, the flow, and you are tested. Test pattern started from my live set. I need visual behind me when I do the DJing or the live performance. I have decided to show binary and zeros and ones, black and white, like a barcode. It's very simple. But then I realized it might be interesting to magnify glass. It's very different. Other things is you observe from the outside, but then you have to be inside of the information and the data. Your iPhone has that kind of pattern. When you amplify visual audio component like 1,000 times, 10,000 times with a magnified glass, the pattern is like that. It's really, really interesting. But
Unmute myself.
Chiffres.
A simple example. Two farmers are trading 17 geese versus 5 sheep. The shepherd owns temporarily enough geese for the sale, willing to give away the sheep. In doing so, trust is an important factor. The farmer will still give away the sheep, anticipating that he will receive the 17 geese whenever he needs them. Modern economics dealing with consumption, capital, debt, and interest as forms of symbolic reproduction relies on trust, speculation, and rhetoric. Thus many of the foundational economic theories come from moral philosophy rather than from mathematics.
Okay. So now I think it would be a good moment to maybe switch to Superglider and take a tiny look at my own approach. So I'm gonna switch the screen. So here's my Superglider code. So first I should say that, of course, this session is not long enough to, it's to be able to get into the syntax and technicalities of Superglider, how it works. So this is not about that. This is just to show how I approach data, for example, in a very simple way. But yes, again, if you're not really familiar with the language and the syntax, then maybe we're not going to really talk about this today. So I'm here. I have some files, some PDF files, CSV files, and I want to sonify them to see. I know how they look, but I also want to see how they sound. For example, I declare the path, so where are my files? And then here I'm using, maybe it's useful if you see I'm sonifying, so see this? Let me know if you can't. So this is the folder of the data that I have. It's just a bunch of files, CSV, text, PDF, research proposal, which is just a PDF of like 3 pages. And I want to see how it sounds. So I come back to Discord, switch the screens. Okay. So in the first section, what I'm doing is mostly what Ikeda was also mentioning, that you take the data from the PDF, you read them as signals, and then you just give binary information, so zeros and ones. And then you load them into a buffer, and then you simply play the buffer. I'm gonna run this, and I'm gonna mute myself. It's a very short sound that is being looped. Be a little bit careful with the levels. I mean, I hope they're fine, but still be a bit careful. So this was the sound of my proposal. Another block that we have here is, okay, so here, instead of me reading from a file, I just made an array of random numbers. Here is my array of random numbers in the post window down right, you see my random numbers that I got, okay? So I want to sonify these numbers. I make a synth def. So this is my synth. This is just reading from the buffer. And then I mute myself again. So since there are random numbers, it's like noise. So if you change the rate, you can just change the rate on the go and then see like how it sounds. But it's just reading from the buffer. So, and since we have random numbers, it's technically noise. So another approach is to read files. For example, I have a text file here. Oh, you can't see it anymore, but I'm going to print it out here so you will see it. But I have a text file, which is just some notes that I took during a lecture. It was the only thing that I had around. It could be anything. It could be a shopping list. It could be a course list, whatever it is. I will take the text file, and I have a function here that makes a loop, and then the file reading process will happen inside of the loop. So if I do this, then you see what was in the text. So it's starting to read from the text and then post it here because I tell it to post it here. So you're going to see, so here you see whatever is on my text file. And then I can also just scramble all the letters, just see the letters are scrambled. So you're dealing with strings, so you can scramble or all kinds of stuff that you find useful for your approach. And then I make two synths, very simple ones, one with impulse and one with dust. And then now here I go to read this file, and then I control the frequency of my synths with the data that I'm getting from the file. So let's see how it sounds. What is happening here is that I'm getting these letters from my class notes file, and then I'm converting them into their ASCII. I might want to look it up. It's a table that, you just might want to look it up. So it's technically, in a very simple and brief way, what it's doing is just taking these letters and then assigning a number to it. So I'm using the numbers to set the frequency. So I'm saying, okay, what is the number for letter T? It's that, then assign it to see how this same data sounds with a different approach. So I had two synths here. We were listening to SND, which is just an impulse. And then now I change it to this, which is a dust. And then I'm just gonna change the weight rate so that we have a different experience. So this ASCII approach seems to be kind of useful. You can easily find the table and work around with it. So, and then at the end here, I found some maybe more complex data. So rather than just being some letters, I took a table of earthquakes. And then I want to see what I can do with that. So I will go back to my full screen. Okay. Here, this is my earthquake file. So we have so many of the magnitude, longitude, depth, data. So when we're dealing with this kind of data, how should we approach it? Of course, the first step is to take a look at what kind of numbers you're getting, or what exactly is the pattern and structure of your data set. And then according to their properties, you find how to express it in the most efficient way, or in the most artistic way, if you like. So the first thing is again, just to, go through your data, see, okay, I have like numbers within this range, and what can I use? Can I use different parameters for like the latitude and the longitude, and all kinds of ideas, which start with observing very well your data set. So I'll go back to SuperGlider. So here, I'm reading the file, which is my earthquakes CSV file, and I'm posting it. So it's just starting to read. This is the first row, this is the second row, blah, 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 and it's just going on forever. We have so many locations. We have the magnitude, latitude, longitude, depth, date, and all kinds of data. So when we're dealing with this kind of data, how should we approach it? Of course, the first step is to take a look at what kind of numbers you're getting, or what exactly is the pattern and structure of your data set. And then according to their properties, you find how to express it in the most efficient way, or in the most artistic way, if you like. So the first thing is again, just to, go through your data, see, okay, I have like numbers within this range, and what can I use? Can I use different parameters for like the latitude and the longitude, and all kinds of ideas, which start with observing very well your data set. So I'll go back to SuperGlider. So here, I'm reading the file, which is my earthquakes CSV file, and I'm posting it. So it's just starting to read. This is the first row, this is the second row, blah, 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 and it's just going on forever. And then I specify the synths. I made 3 synths. They're all quite simple, so nothing really crazy is going on. We have some binary operations, but mostly you can just put like oscillators, and then just to use them, and just, you can start from a very simple, straightforward way, and then just to play around with it, see how it goes, observe how it turned out. So these are my synths. And then here I have a loop that is going through the rows that I want, taking the data, assigning to what I want. Okay, so I want the magnitude, the tidal, the longitude, the latitude. and then I tell it where each of them are. So I say magnitude is on the first column. Yes, yeah, the first column. So here's the row, and this is the column, I guess. So you go like this to specify what the data that you're getting, where is it? And like if you're on the second row, then it's the latitude, for example. So this is just telling it where they are, and to post everything that you see, just post it, everything you get, so I can see it in the post window. And then here I have an envelope, and then, okay, so in this case, not even using the synths, we can just make something inside the loop, just to use our synth inside the loop, so that it's just calling what it should. This one sounds interesting, so we're gonna listen to it for a couple of minutes. I'll mute myself. So it was started.